4 is being shortened. We're not going over all of it. We're just going over the very, 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 very basic idea of 6-4. So you guys have your normal 6-3 homework and then just like a shortened version of 6-4, both of which are due tomorrow. However, we're also having a work period tomorrow because this is all that we're covering in chapter 6. 6-1, 6-2, 6-3, and just a little bit of 6-4, and that is all we're covering in chapter 6. So tomorrow is a troubleshooting day. But that's also meaning it's a review day, which also means that we're finishing up chapter 6 with a quest on Thursday. So as we're trying to just kind of troubleshoot the rest of 6-3 today, you guys were trying to plug this into your calculator in degree mode, and I was just saying, hey, this is where we ended last time. Can you get these numbers in there? First of all, what formulas are we using? We're using the ones on this page that say, little despicable me dude says a vector is magnitude and direction, but man, it's so much easier to use components than to use triangles. Triangles, I could play with them, and Noah was even trying to describe about how we were repositioning a vector and thinking about the overall resultant force or direction or magnitude or any of that sort of stuff. But technically, the math is so much easier if we have components. I think, Natalie, you were the one that was like, I thought we were just adding them. We are, but this is what it means. But this over here, for people that are online or listening to this video at a different time, this over here is going to involve a lot of tricky, like, parallel lines and transversals that are cutting and same side that are, like, supplementary, and solving with law of sines, law of cosines, the triangle, to figure out what this length is, and then using my tangent inverse to figure out what that direction is. Or we could just say, hey, if we have the components, let's add them together and then use those. The components make the math easier, but we need to be able to do it. And so this problem didn't give me components. I had to make them myself, and the way I make components is using right triangle trigonometry. Right triangle math. I can get my A by plugging into this formula. I can get my B by plugging into this formula. I can get my components by plugging into this formula. So what I did was 50 cosine 30, 50 sine 30, and that gave me the components for the first one, or 30 cosine 110, 30 sine 110. I'm plugging in, and I got lazy because I didn't want to write out all the decimals. But the goal was, like Noah said, technically, to figure out what happens when we move one of the vectors. I'm trying to find the resultant. I would do u plus v, which means let's get the v over here, an equal vector which has the exact same slant, the exact same length, and let's ask ourselves, what's the overall from beginning to end of the situation, the overall resultant? That's what I'm trying to find. But the geometry, the trigonometry that would be involved in finding this length right here would be really rough. And so we say, hey, can we do a shortcut? And the answer is yes, if you use your formulas. So then when I add down the horizontal component with the horizontal component, or add the vertical component plus the vertical component, where were all these numbers coming from? Were you guys plugging in sines and cosines to your calculator?
Yes, yes.
Now, what was I doing, though, in these numbers that you guys were actually trying to solve down here? Because these numbers, the components, do not match the actual final answers. What are these guys? Thank you. What are these guys? Why am I labeling this one the magnitude of R, and why am I labeling this one the theta of R? It is the magnitude and direction. That's what they were asking, but what did I do to get there? What was the math that was required? Brian Corian. Oh, that's at lunchtime. Sorry, I thought you were raising your head to answer the question. Chris, do you know what math I was doing to get here? No. Ryan Noonan?
I thought find the magnitude first of the resultant, like given like the x's and the y's, or the i's and j's, and like the 50 cosine 30. Or sorry, the 25.
Students, this is Dr. Choi. I just wanted to make a quick announcement for chapel today.
Okay, so we're adding u1 plus cosine 110, and that's where you get the 33.
And where are these little guys coming from again, real fast?
The vectors.
Yeah, exactly. The vectors and the magnitudes and directions plugging into our formulas for all the A's being put together.
And then cosine is horizontal, correct?
Yes, cosine's horizontal, sine is vertical.
Okay. So then that's where you get the 33.04, and then if you do U2 plus UV, or V2, then you get the 53.19.
Is it frozen? Can you guys not see
I
it?
think it should be.
Wait, why is it negative 22?
It should be
Why?
33.
Oh, because you didn't do sine.
You're not in.
Yeah, because I teach multiple classes, right? Good catch, though. And why would negative not make sense? Noah, with what you realized of what we're supposed to be doing, Noah said, like, hey, remember, we're supposed to be finding this guy. Can anybody realize why a negative, besides the fact that you see the answers on the screen, why does a negative not make sense for him? It's in the first quadrant. In the first quadrant, everything should be what? So I'm going to come back really quickly and fix that. And while I fix that, I need to come down here. Cool. Is that better?
Yep.
Awesome. Let me stow that as A, because that's going to be our horizontal component of our resultant vector, right? Take the U1. Jackson, you said that well. I can label this a little bit better, huh? The U1 and the U2. U1 plus V1 makes the horizontal component. Cool. And then you said I need to change it to signs for the vertical component, right? You guys hearing this vocab he's using also? Sine. Ooh, quite outstanding. Go team. I'm going to stow it away as B. Okay, Jackson, once I have these components, now what?
You want to plug it into the formula, U1 plus U2 squared plus V1 plus V2 squared.
And what, I mean, that is a formula we can memorize over here, right? We have our horizontal squared plus vertical squared equals magnitude squared. But what is this formula at the end of the day? Pythagorean. Yeah, it's not meant to be something crazy and trippy and weird. So when I have my components of my R, which we found without doing any law of sines, any law of cosines, we could have, but I thought, components sound easier, and you guys agreed with me last week as well. When I do the Pythagorean theorem, what am I going to solve for? Yeah, the hypotenuse, which is the same thing as the magnitude. Does that make sense? The same thing as the magnitude of my resultant vector. So I did it with all the nasty decimals. You could also do it with the nice little letters. And hey, so the magnitude is the hypotenuse of my components. Ryan Union, what's up, kid?
At the beginning, when you're finding like 33.04 and stuff, and like you're doing a 50 cosine 30 plus 30 cosine 110, why do you add them instead of subtracting them? Like, wouldn't it be like x2 minus x1?
You're thinking of trying to find the distance between. Instead, I'm trying to think of, if you want to think about it on the picture, I'm thinking the first vector moves me horizontally this way, and then the second vector moves me technically horizontally this way. And so I'm adding a positive with a negative, which will result in the backwards motion, right? And then the same thing is going to go with my vertical, as far as I'm going to add what the first vector accomplished plus add the vertical of what the second vector accomplished, and I'll end up with the overall vertical change. So I'm not finding the distance between. Instead, I'm trying to combine the two together, which is the exact same thing that a resultant is, in the sense that the resultant is U plus V. Does that make sense?
Yes, you can find like the total distance it moves in that direction.
Exactly. The 5 hands around the room, what's wrong? All separate questions? Bathroom fast, yeah. Andy, go ahead.
So you know how you redrew like the triangle on the right?
The yellow, green, or blue? Oh, this guy?
Yeah. So what is that like representing? Like what on like the yellow, green, and blue? Like what is that representing?
This is representing, remember how Noah, the first thing today, he was like, oh, hey, aren't you moving a vector and then you're drawing the resultant? And he was totally right, but last time I totally, oh, that doesn't cover it up. That's a bummer. Last time I was not doing the vector diagram. I was saying we can avoid the vector diagram by just using our formulas and saying, what are your components, what are your components, and let's add them together. So I was just saying, hey, forget the picture altogether and just think about who is this guy at the end instead of all the steps to the process.
Okay, so you just like redrew your own triangle kind of.
Yeah, I said it's positive, positive, so I said, oh, hey, this is the overall effect. Because in other vector diagrams, we could very easily have like a u vector, and then we could have like a v vector, and then we could have like a w vector, and then we could have like a z vector, and the resultant doesn't care about all of this. I mean, it does in the sense of it's beginning to end, but the resultant just says, hey, I'm here. I'm at the very beginning to the very end, so if I do all that addition, I can kind of land here without doing all the crazy parallel lines and geometry, transversals, alternate interior angles, etc.
Also, how did you figure out like what you need to like plug into each side and angle? Like, you know how you have the
Each side and
no,
angle.
like on the triangle, you know how you have like the R2, the theta, and like the vector.
Oh, I was using a general breakdown of a vector.
Oh, okay.
And the general breakdown of a vector says I can talk about him like the little Despicable Me guy does with direction and magnitude, or I can talk about him in terms of what's happening horizontally and what's happening vertically. Does that kind of make sense?
Yeah, that makes sense.
Now I'm naming it, I think Jackson might have seen this in the book as well, but Jackson was talking about how we can call like U1, U2, V1, V2. It's just a way to use the letters, but still have like an A, B idea, because I can't do like A, B, C, D, E, F. I could, but it starts to get confusing. So we use these little subscripts to kind of help us out. Is that not at lunchtime?
It says 9:05.
Interesting. Okay.
Sorry.
No, do what you gotta do, I guess. Thanks, bud. So that was plugging into all the different formulas. There were a couple things that showed up last time that I kind of breezed over with this whole weird I and J. And so since Jackson was using really good terminology, oh, the one math thing I didn't do. We did Pythagorean theorem, sorry. The one thing I didn't do was this bottom one. Why on earth am I doing a tangent inverse of B over A? I have the opposite, I have the adjacent, and when I do a tangent inverse, I can make it back to the first quadrant angle that matches it, and hence I have my magnitude and direction, which is what I started with, but of my resultant as well. These I's and J's, guys, it's not like this huge, crazy idea. These I's and J's just say, hey, you know how we do this whole A and B thing? And I just kind of like reminded / solidified what some of you guys might have been seeing. That we could say like, oh hey, but for a vector v, we could call that A v1, that B v2, just to kind of make it specific to that one specific vector. I could go ahead and think about, okay, what would that be? So if they were to give me something like this guy with a 7 and a 5, and I say, okay, it's over 7 and it's up 5, for our example, I could say, cool, another way of talking about this guy is literally just putting his components in. But down here, I can also say the exact same thing, but using what we call as unit vectors. This little I and this little j, they're not imaginary numbers. Little I says, hey, guess what? I'm the most basic horizontal vector. I go over 1, up and down none. J says I go up 1, over none. And that's who these little guys are. And so when I start, I put 7, 7 instead of 7, 5. But when I put numbers in front of these guys, I'm like, hey, I'm talking about a vector, and I'm talking about a vector in a specific direction. I'm just talking about them in a different way. But for you guys to understand, these are actually the same exact thing. Both of them are describing vectors that have a horizontal change of, 7, a vertical change of 5. One uses what we call side carets, and the other uses what we call unit vectors. So when you see them, that's who they are. But there's a special name for these different notations as well. And I think it's on the next screen, to be honest, but I can kind of write it here, and some of you might not even need to write the next screen. This one is just talking about, we usually call it component form, is with the side carets. And then this guy down here, we call it linear combination form. We have component form with the little side carets, linear combination form with the i's and j's. But basically, they're the exact same thing. So when you come over here, and if we were to talk about, I mean, we could do these types of problems, but I think what's probably the trickiest part would be something like this that says find the unit vector of u. So instead of having us like write down another vector, I'm going to go ahead and kind of just take us to this example so we can see one type of problem that might kind of mess you up in WebAssign. Remember, 6.3 has been extended till tomorrow along with 6.4. I just want to show you guys this idea right here, and then I'm going to go ahead to 6.4 and show you the most basic idea with that, and we'll be done if we can stay focused for 5 more minutes, okay? And then we can have troubleshooting work period tomorrow, and I can help with whatever. Does that make sense? Okay. So, if we were to be given linear combinations, oh my goodness, it's ridiculous. No, it's not. No, it's not. Just check it. If I wanted, we would get some little bold letters to become vectors, because if we're handwriting, right, putting little vector arrows everywhere. If I was to want double V in linear combination form, because the little components are still being shown, I can just go ahead and double. They're like components, just they have i's and j's. But the math is as easy as components. It just looks a little different. But just for you guys to realize, it's the exact same thing as the math that you liked last time. Is that okay? Math look good? Cool. If it's in components, it's nice and easy. How about u plus v then? You guys take it away. If it's as easy as combining my terms, what's u plus v?
4i.
Yeah, got it, right? Think of the understood one, positives, positives, negatives take away. Perfect. It'd be the same thing as what in component form? And these vectors, if you wanted to visualize them, couldn't we, starting from the origin, because they don't give us like an initial point, starting from the origin, we go like over 6 and then like down 4, right? And my vector would be for double V from beginning to end of that motion. Or for number 2, I would be in the first quadrant because I have a positive and a positive, so over 4, up 3. Ah, that looks congruent. Sorry. Oh, Santa. Start from the origin if they don't tell us another place to start, and that would be my u plus v. Are we okay, cool kids?
Yep.
Okay. But what if they say unit vector? Unit vector, I need the vector length of the unit. I'm going to put n for unit just because I'm already using u. I need the length to be 1, which makes it all awkward. So let me show you how to always do unit vector. For the unit vector, all I need to do is take v1, take v2, and scale them back. Scaling back in math just means divide, and what we're going to divide by every single time is the magnitude of the vector that's not 1. So watch me utilize it right here. I'm going to say the unit vector of u is going to equal, take u, I'm going to do 1 over and 5 over. I'm going to start there. I'm going to take the 1 and 5 that's right up here. I'm going to go ahead and go off to the side real fast and say, okay, what is the magnitude of u using Pythagorean theorem? So 1 squared plus 5 squared is root 26. And I just say, well, hey, he's definitely not 1. He's root 26, which is 5 point something. I just need to scale everybody back by that root 26. And I will have my final unit vector, which could be written like that, or it could be written like, maybe you guys can see where the nice snazzy form would come from if they rationalize their denominators. Either one's okay. One's simplified, the other one's not. One's in component, the other one's not. But what I'm doing is I'm scaling back the current size by a magnitude, and I get to make that final length 1. Brandon.
For the unit vector for the bottom problem, I'm using use vector.
Oh, I was just doing a general unit vector formula, and then U was the guy that they told me, yeah, so I used U for this guy. So that's just a general notation. But they said U, if it was V, then it would have been V. So if you guys want to make it for this one, I guess you could say U. I was just trying to make it for any vector V. Now I did say that I wanted to not only look at the final content of 6.3, but also the one idea of 6.4, called the dot product. The one idea of 6.4 that we're going to cover. And the dot product says, I see the time, Andy, you're going to have to ask me after the bell rings. The dot product says, basically, I am a very, 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 very special quantity in vector math that gets used for a lot, that we're not going to really focus too much on the getting used part, but we are going to see, okay, it's a thing where I multiply the U1, V1, and I add the U2, V2. There is no multiplication of vectors. That's not a thing, unless we're doubling or tripling, but not like a vector times a vector. So if you ever see it, it's this guy called the dot product. We're just going to play with the dot product and not really any of its applications. So I'm guessing tomorrow you guys hopefully have all the basic homework done, and you're going to come with word problems started, but probably not finished because you probably get a little overwhelmed. And that's what tomorrow's for. Is that cool? Vector troubleshooting tomorrow. Bye, guys.
We're not allowed to go to our locker. Are you gonna post like a receipt thing for